Welcome to ClickMyProject.com. Now we discuss about the product for novel narrowband balanced bandpass filter using rectangular dielectric resonator. The abstract for the product. Recently the balanced circuit have been widely used and gained much attention for their excellent performance of high immunity against hostile environmental noise when comparing with unbalanced counterparts with single-ended input-output ports. According to the balanced bandpass filter plays a key role in a modern differential communication system, and there has been widely explored for performance improvement. Over the past few years, several classes or balanced filter have been reported developed with good performance using the printed circuit boards technology and the low temperature coefficient ceramic technology. However, they are hardly employment in narrowband system due to their low Q factor limitation. Recently, a few balanced bandpass filter using a substrate integrate waveguide have been receiving the tremendously increasing attention as the SIW resonator showcase improved the Q factor while maintaining the low cost and good integrations and so on. According to the balanced bandpass filter with less than 5 to 3% of functional bandwidth. For the first time, the novel narrowband balanced bandpass filter using two coupled rectangular dielectric resonator is proposed. According to electromagnetic field properties of the dielectric resonator, the TE1 mode as a dominant mode of the DER can be differentially excited for constructing the fundamental passband and of the balanced bandpass filter. Meanwhile, the fundamental passband of the balanced bandpass filter, the TM11 mode of the DR functions as the common mode response in the design, is tuned far away from TE in spectrum by optimizing the DR size so that the common mode suppression in the differential passband and improved significantly. To validate the proposed design concept as a second order narrowband balanced bandpass filter is designed, fabricated and measured. Next we see the flow diagram for the antenna design. We implement the antenna design using the HFSS software. This software to implement the high frequency synthesis simulator based frequency development and the bandwidth calculation to be all the designs and developments to be included in the HFSS software. So first we open the new HFSS software and new project design in our 3D model based designs. Then create a new project design. Then go to first we create the any one of the antenna. First we choose the substrate model, and to analyze the substrate model and the dielectric constant value and permittivity value and the dielectric substrate modeling type, all the things to be noted. Then we select and create the patterns for and the shapes for our substrate model, because example for circular or rectangular or square or triangular based substrate model used in our any one of the HFSS modeling designs. Then we apply the which substrate model to be implemented. Example for Roger 54003 or 5005. So then to apply the substrate model, then we go to the assign substrate material type. The material is represents the same like a Roger material, and we go to the patch model design. Whatever patch model we use, the circular, square or rectangular patch model to be implemented in our designs, and we using the polyplane for rectangular shape cut, all the things, and we add and subtract the implement design, and to connect the what are the patch model implement in our secured diagonal patterns, and we implement the XYZ dimension based substrate model design in our secured selected new project. Then we go to the to design the bottom patch and top patch design. Every model consists of the ground plane and the top plane structure for our required patch wise designs. When the substrate to be included and the multiple substrate model and the 3-layer model and all the things to be designed in the first design based process. In every antenna design, we implement first the design phase completions process to be calculated, then we go to the final design phase process. After design process to be completed, then we go to the analyze setup work for every antenna design. The analyze setup mainly focused by the boundary wise designs and the excitation wise designs in our field setup. Whenever you use the electrical field and we use the wave port model, and the magnetic field we use the step up port model for overall antenna designs. These designs to be applied for the frequency range. Then to set the frequency for a start and stop frequency and the solution frequency. The solution frequency to be changed based on the antenna model designs, and whatever we working the full bandwidth and to coverage with the center frequency range for our required solution frequency model. Then to set up all the frequency model and to run and the overall process. Then if the run to calculate the S parameter, and it's like return losses for our required antenna design, then we go to the empty boundary box to be set up for our required antenna model design, and to set the radiation pattern. This radiation pattern to set the pattern wise model for our required 360 and 180 degree pi and theta value for set up for our overall radiation pattern. Then to calculate the radiation pattern graph and the polar plot graph and the gain level and all the things VSWR, each and every analysis for required antenna design to be calculated for our required model, final model. These are the final flow diagram for the antenna design process. Finally, we see the output for the product. These are the project to ANSOF to HFSS file. Just double click the file and open the new software. These are the HFSS, our final output antenna design due in the HFSS software. These are the final model design for our overall process. Then open the 14th is the final designs. This design to implement the two layer for a required substrate model and the vacuum layer to be used in our air material to the radiation boundary box, and cylinder for required PEC material for using the feeder point to ground plane structure connections, and this material for our two first to final separate, and the box 2 is a separate substrate for required patch model design. These are the required four-way waveguide filtering concepts, and these are the rectangular patch model for ABC structure connectivity. These are the overall ground plane structure and the feeder point for each and every 4 sections, the 4 feeder point section. These are the final simulation design for our required output functions. These are the filtering model. Then simulate and listen. This is our overall final designs. These are the final designs model. Then we go to analyze the report for our required modeling. These are the narrowband structure. The narrowband to be presented for the 2.42 to 3.9 working for frequency for narrowband implementation. These are the narrowband for up to -20 dB. The narrowband working level to be implemented in the enhancement model. These are the final output for the product.